In fact, I have non-gray hair. I have regular hair back because of the radiation, actually. Anyway, that's a long story. We're not going to go into the details. Okay, so some administrative issues. One, I'm going to post my office hours on the website, but they're going to be tonight from 7 to 9, tomorrow from 6 to 7:30, and then Thursday from 1 to 3. I'll post all those, but I'm giving you different time spots. Evenings, I think, is when people generally work on homework. So if you have questions, you can ask me in the evening, but also I'll have the office hours during the day on Thursday, the day before your quiz. Remember that your homework quiz allows you to bring in your homework and look at it. You can look at your class notes, you can look at everything. And they're basically going to be regeneration of homework problems. So they're not going to be just recopy a homework problem, but rather if you understand the homework problem, you should be able to answer the quiz question sort of deal. Are there any questions about any of that before we, yes?
That's not the entire thing that we do on Thursday, right? That's just a little...
Oh, no, sorry, that'll be the first 15 minutes of class. That'll be the first 15 minutes, and then we'll have an hour lecture afterwards. Yeah, sorry, if you've never done this, yeah, it's not obvious. Other questions? Yes?
So if I take all my notes and do my homework on Surface, should I not do that? And then instead do it on paper?
No, you can, so you can bring in that's something you can't use. You can't use a computer. But you can use a computer to look at your notes. That's fine. I just don't want you Googling things. So yeah, I'll walk around and kind of monitor you, and if you're Googling stuff, I'll slap you hard. Yeah. I guess I could take it out on your grade, but I think I'm just gonna slap you.
We should probably cut that out before posting it on YouTube.
Oh no, this is going on YouTube. This is going on YouTube. Oh wait, so I get so confused because I see the Zoom screen, which is always kind of tilted. Oh, hi, Ross. And then there's the screen that the camera is recording. Anyway, it's all good. Any other questions? Are we ready to go?
Yeah. I do have one question.
Oh yeah, go for it.
How am I going to do the test?
Oh, you'll do it. You'll do it like we did at the end of last. You took particle physics, so we'll do it like we did. I'll open it up on the website, and you'll just work on it for 15 minutes.
Oh, okay. So it's through an email.
Yeah. Well, no, it won't be through email. I'll talk to you about it later.
Okay. Is there one? Is there one today?
No, there's not one today.
Okay. Thank you.
Yeah, and remember that I'm evolving your homework based on how much we get through, so I'll add another 2 questions to the homework tonight, okay? Covering what we do today during class, depending on how far we get, okay? Does that make sense? All right, good. Okay, so we ended last time talking about linear transformations, and I just want to stop for a moment and remind you all of what we're talking about. We've been talking about vector spaces, and unfortunately you've encountered vector spaces numerous times in physics. Of course, we're trying to define them from the get-go here. It's a little bit different, but one of the things that I think it's easy to default your thinking to is, oh, he's talking about a vector space which is spread over space-time and shit like that. Okay, now that's not what I'm talking about. That's technically a vector field. The field version being that it's got a vector associated with each point in the space or space-time, okay? And that is a very important part of physics. But what I'm defining for you right now and working with is simply a single vector space. So this is what could be defined at a point in space. And the thing is when you want to extend that to defining the vector space at all points throughout the space or space-time, then you have some difficult issues that you have to face, which I might or might not cover in this course, but I will definitely cover when I teach general relativity next semester. But essentially, you have to be really careful because the basis that you're using to describe your vectors could actually change as you move throughout space-time. And so comparing vectors at different points becomes very, very tricky. Okay? And this actually forms the backbone of both particle physics and general relativity to a certain degree. Okay? But what we're doing now is we're not talking about fields of vectors. like the electric and magnetic field. We're just talking about a single vector space, so a single collection of vectors all pointing away from the origin, if you will. Okay, so in the definition here, I just want to remind you, you start out with vectors in a space V, you act on them with the linear operator A, and you get back vectors in the space V. The linear operator is not carrying us from one collection of vectors to a different one. That's going to be important a little bit later on, okay? Furthermore, remember how I said with vectors we don't have a natural product of two vectors yet? Remember, we haven't introduced an inner product yet. However, for linear transformations or linear operators, there is a natural product. Because if you think about it, if I wanted to figure out what ABX was, first of all, I should realize that BX is taking vectors in V and giving me back vectors in V. So these are just vectors in V, which A can then act on. Okay? So the product here is more naturally defined. It comes with the definition of a linear transformation versus the product associated with vectors, which we have to put into the story, and we haven't done that yet. Okay? We will down the road. Okay, we looked at some examples last time, but we're gonna go over one of the headachy things in just a minute. But I just want to finish up the list of important aspects of linear transformations. So first of all, there's the zero transformation. What does that give you?
It just gives the same.
It gives you zero, people. Oh, yeah. I so made myself mad. I walked out of the house, came here, got here, and realized I forgot the cards.
Oh, no.
Yeah, I know. So I'm just going to point. And I'll point there. Okay, now, it's zero, okay? And identity on X? X, right. Okay, is this the number zero?
Not necessarily.
Is this the number one?
Not necessarily.
Does the number zero work? If I take a vector and I multiply it by zero, don't I get the zero vector? If I take the vector X with all its components and I multiply the whole thing by 1, don't I just get back the vector? So why isn't this just the number 0 and the number 1?
It could be other things.
Yeah,
It could be.
because X could be polynomials.
If you multiply it by 0, you'll get 0.
I guess it would still work.
Huh.
But it doesn't have, yeah, it doesn't have to be zero. Like, doesn't it just zero is a possibility of a linear transformation?
0 is a possibility of linear transformation, but I'm just asking, it seems like the number 0 would work here. I mean, it would take all the components of vectors setting the vector equal to 0.
So you guys zero in our vector space?
I don't know, is it?
What, so if it's not, then that's not going to help us.
Yeah, it is. Okay, so remember one of the rules of vector spaces is that you have this additive inverse between vectors, and this gives you 0. Okay, this gives you this 0 thing, but these are multi-component vectors, so this is a multi-component 0. Okay? And similarly, if we have oh no, sorry, not vectors at all. Sorry, I'm talking about linear transformations. Sorry, whatever structure linear transformations have, 0 has the same structure. Okay, so if these are not scalars, if there's some complicated operator like a derivative operator, then this has got to have a similar structure. Similarly, these are two of the operators multiplied together, and they're giving you the identity. So the identity's got to have whatever structure these A's have. Okay, so no numbers don't work, unless, of course, your set of operators is just acting on a number, and then the operators themselves are numbers. Okay, and there is a set of linear transformation properties that are important, and we'll just throw these up here. A0, of course, commutes with A commutes with 0, sorry, A commutes with I. The linear transformations are linear with using the multiplicative rule between the linear transformations. That's a bit different than what you see up here, because this is defined in terms of the action of the linear transformation on vectors. Okay, this is saying using the product of linear transformations, you have a linearity. Associativity. And then you have the action of a scalar. Or sorry, an element of the field. Okay? But note, in all of this, AB equals BA is not required. Okay? So we've got all this linear properties, associative properties, but we do not require linear transformations to commute with each other. And that's a very important open doorway to more interesting transformations than those which strictly commute with each other. Okay. Any questions about this stuff I've got up here?
So are linear transformations like necessarily a group? Kind of seems
Do they
like
have to
that.
have inverses?
Linear transformations form, well, if you take all of the, so this is actually what I'm about to say, but if you take a vector space and you consider the set of all possible linear transformations of that vector space, then that set of linear transformations itself forms a vector space.
Oh, right.
Yeah, but I'm going to get to that in just a second.
Circle.
Okay, so what I want to talk, so I'm going to erase all this because I'm going to need room on the board to get to the evil part of the transformation story. No, it's actually one of the most important aspects of the transformation story, and that is the subject of inverses. Okay, so for vectors, any x on the vector space V has an x inverse, which is on V, which is just minus x. Okay? However, what about linear transformations? What's interesting about linear transformations is we have the ability to add them, and we can multiply them. So if you want to talk about the inverse of a linear transformation, are you talking about the inverse operation when you're summing them or when you're multiplying them? With vectors, we only have addition so far, so this is the only inverse to think about. Okay? Well, first of all, as I said before, if I take a vector space and I look at the space of all linear transformations that act on the vector space, then that vector space, or that set of transformations, forms a vector space. So for a vector space V, all, and this is not a subset, this is all of them, every linear transformation you can possibly write down, all linear transformations, whoops, form a vector space. Goodness. V prime. Such that, well, you know how this goes. V B prime and plus forms an abelian group with identity equals 0. And for every f, or sorry, for every alpha on the field over which these are defined, there exists a transformation alpha A on the vector space V prime, where, and these are all of the rules that we talked about for defining vector spaces, except now we're using linear transformations as the vectors in the vector space. Whoops, no, that's B. Goodness. Okay, this looks just like the definition we gave for a vector space. I'm just showing you that the set of all linear transformations satisfy this if they're working on the same vector space. Okay?
For B, the subscript B there, did you mean to say equals alpha A plus alpha B?
Oh, yeah, sorry. Thank you. Oh, goodness. Okay, so obviously, if I want to ask if there's an inverse to a linear transformation A, is there? There's a sum and a multiplication. Which one is there, definitely?
For the sum.
It's for the sum, right? I mean, it forms a vector space, okay? So we have the additive sum, or the additive inverse, which is just minus A, okay? So really where it gets interesting, and where the answer to the question is not always yes, is the multiplicative inverse, okay? So we're just going to go ahead, the multiplicative inverse you might define in terms of whatever your composition operator is, but we're just going to call this A inverse, okay? Whenever I write A inverse, I'm talking about the multiplicative inverse, because the summative inverse is always just minus A, okay? So here we go. Let me erase this. Yeah. And we'll get something useful down and then look at some examples. And I want to stress to you all, you've seen inverses before, you know what to look for if you want to know if something has an inverse. Well, right now, remember, I have not identified linear transformations with matrices yet. I will. But all of the properties that I'm going to give you before I associate them with matrices, you can think about them independent of matrices. Of course, there are matrix versions of lots of the properties. We'll talk about the determinant a little bit later on, okay? But I just want you to realize linear transformations do not have to be cast in terms of matrices. As we saw last time, I talked about the derivative operator acting on the space Pn. Okay, that was completely well defined. It satisfied all the defining properties of a linear transformation. It's a derivative. Okay? All right, so here we go. If a linear transformation A has both the following properties, then A inverse exists. A. If the two vectors that you're working with X, so if I have a vector space on which the linear transformations act, if I choose two different vectors, then the outcome of applying a single linear transformation A to each of those vectors must give you different results. You can turn that around and say if a linear transformation on two vectors gives you the same result, then the vectors must be the same. Those are both saying the same thing. Okay? And B, for every y on the vector space V, there exists an x on V such that the linear transformation on x gives rise to y. Okay? Now, I'm going to use a matrix, but I don't have to, but I'm just going to use a matrix to illustrate these two properties. So I want you to consider, as an example, a rotation operator. So this is going to just transform vectors in R2, say. You could transform vectors in R3 with it if you expand it up to 3 by 3, but we're just going to use a 2 by 2 matrix. And whether you put the plus or minus on the off-diagonal terms entirely depends on whether you're doing active versus passive, so don't worry about that. So this is a linear transformation, which most of you should be very familiar with. And what I want to do, first of all, you all know this has an inverse. It's a rotation. You rotate it back. Okay, but what I would like to do is prove that this has an inverse using these two properties. Okay? So let's start with property A. So if X is a two-component vector AB, and Y is a two-component vector CD, then we have R theta on X is A cosine theta minus B sine theta, A sine theta plus B cosine theta. Okay, I'm literally just multiplying this little vector by this matrix. That's pretty trivial. And R theta Y is C cosine theta minus D sine theta, C sine theta plus D cosine theta. Okay? Now what I'm going to do is I'm going to use this version. Okay? So I want to say R theta X equals R theta Y. So what I of course get is A cosine theta minus B sine theta equals C cosine theta minus D sine theta. And then A sine theta plus B cosine theta equals C sine theta plus D cosine theta. This is just demanding that these two be the same. Okay? It's pretty reasonable. So we take this and rearrange it, and we get A minus C cosine theta equals B minus D sine theta, A minus C sine theta equals minus D minus B. Hold on, nope, wait a second. No. B minus D. I have it written wrong in my notes. Cosine theta. Okay. Everybody on board? divide these two equations. Divide the left side by the right side, or sorry, divide the left side of this one by the left side of this, and the right side of this one by the right side of this one, and we get cotangent theta equals minus tangent theta. Is that ever true? No. So under what circumstance are these equations valid?
When A equals C and B equals D.
Exactly, when A equals C and B equals D. But that's saying if these rotated vectors are the same, then the original vectors you're rotating have to be the same. That's condition A. Okay? Everybody on board? Okay, good. For B, well, if I take y as AB, then x is just going to be A cosine theta plus B sine theta minus A sine theta plus B cosine theta. Such that the rotation of this gives me back y. Okay? So r theta times x gives me y. Any questions? Okay, so let's divorce ourselves from matrices for a moment. We got to stop talking about matrices. Too damn many matrices. So let's talk about another example, which I already know a bit about. D on Pn, and we'll just use D on P2. So this is the derivative operator acting on P2. I mean, this was labeled K and K prime and everything, but I'm just going to talk about a single derivative. Okay? So let's ask, is A satisfied? What do you think? Yes?
I'm thinking about like if x and y were constants and you were taking like a first derivative, you could get that they end up being like 0, right?
Those should be different constants, yeah.
So, which are you using, this or this? Left or right?
Probably the first one. So I'm
Okay.
saying like if x is a constant and y is a constant, you put like the first derivative of both of those, then they're both 0.
Yes, yes,
Yeah.
exactly. I mean, I actually threw in a t squared, but that's exactly the right thing. So I say x equals t squared plus 2, y equals t squared plus 3, but you don't need the t squared in there, that's just there to fool you.
I
Yeah.
just have a quick question.
Hold on, Ross, hold on for a second, Ross. Okay, so you find that even though x is not equal to y, ax is equal to ay.
So it's not linear. Or
So-
no, then there's not an inverse.
Right. So this is telling me there's not inverse. Go ahead, Ross.
I'm so sorry. I just can't see the board.
Oh, you can't see the board.
Yeah, it's kind of blurry. Would you mind bringing it a little closer, maybe?
Oh boy.
You can turn the lights again.
Yeah, I think it's the.
Sorry.
Okay, well, he said it's blurry.
You should write down which ones are.
That didn't do anything.
That did.
Oh, no, that did.
You turned off the wrong lights.
Okay, let me see how it looks. I mean, I don't know. Does that look any better?
It looks a bit better, but I still am having a lot of trouble reading it.
Yeah, unfortunately, this is standing on this coat rack, actually. which the camera videotaping this to put on YouTube is also on, and if I move one, then the other one moves. So for today, you might just have to deal with this, and then next time I'll set it up differently so that I can actually, yes?
I just thought, because I did online on Thursday, and I also didn't like it. Can you maybe post the lecture notes before lecture so we can follow along with the notes while I'm hearing you say it?
Oh. You did it on Zoom or you did it on YouTube?
Did it on Zoom on Thursday.
Okay. Sure, I'll try that. Yeah, I'll try that. Okay, can you guys see okay? All right, sorry. Sorry, Ross.
No,
Okay.
I'm sorry to interrupt the class.
No, it's fine. Okay, so there are names for these conditions. The name of this is largely injective, or one-to-one. And this is surjective. Or onto. Okay? Oh, sorry, hold on, I'm not done. Before I get to injective and surjective, with D on P2, we can also show that this B is invalidated. If we take y equals t to the n, then there exists no, sorry, and this should be t to the 2. There exists no x such that dx equals y. Okay? Because if you're taking the derivative, you got to have a t cubed in order for the derivative to come out t squared, but t cubed's not on the space. Okay? So this example fails both of these. All right? Okay. So D has no inverse on Pn, and I want to stress to you all that the examples and the topics that I'm talking about right now is largely finite dimensional vector spaces. We will eventually relax that to infinite dimensional, and certain things will change. You got a question?
Yeah, by disproving either case A or case B, all you really show is that A inverse doesn't necessarily exist.
It doesn't
If you
exist.
disprove them. It doesn't it definitely does not exist.
Yes.
Okay.
Yeah. It definitely doesn't exist. Okay, so consider the following. This is another way of saying this. Hold on a second. Yeah. So these constitute a definition of inverses, and then based on this, we can derive the following theorem. If AX equals 0, then if this implies that x equals 0, then A inverse exists. That is a theorem, which we can derive from the definition. So let's do that really quickly. So let's start with AX equals AY implies x equals y. Okay, so we're using this version of part A. Then A is invertible. But then we can say, okay, well, AX minus AY equals 0 if AX equals AY. Okay? But using the linearity of linear transformations, this is A acting on x minus y. But if A is invertible, that means that this has to be 0. y. Okay? So, I mean, really and truthfully, what you should focus on is this right here. Because this is the statement that if A acting on something equals 0, then this thing is 0. That's what this is saying. Okay? Now, for finite dimensional vector spaces, if you're not working in an infinite dimensional vector space, it turns out that A is all you need in order to demonstrate that, and by A I mean little a. Little a being satisfied means that A has an inverse. You don't have to worry about B. Similarly, instead of little a, you can just use this. Okay? Now let me explain to you why. First of all, A maps X on V to Y on V. Okay? The only way, so let me come back to injective and surjective for a moment, and then I'll use these in the discussion here. So injective means one-to-one. Okay, so if I have a space and I have a map, a one-to-one map, means that for every element in this space, it's mapped to a distinct element in this space. Okay? A surjective map means that every element in this space can be mapped from an element in this space. Okay, so let me show you a non-surjective map. Okay, where there's some element of this space which cannot be gotten by starting with a point here and mapping over. Okay, so that's onto. It's basically you're taking everything here and you're transforming it and you're getting everything over here, not just a part of it. Okay, those are the words one-to-one and onto, or injective and surjective. However,
Question.
yeah,
So this is basic, but the dots mean injective as long as there's the same number and the arrows are surjective. Is that correct understanding?
no, so the function is a map from points in this space to points in this space. The function can be one-to-one and it can be surjective.
Okay.
And that is based on what is the outcome of applying the function to each point in the initial space.
Okay.
So for example, what might happen if it's not one-to-one? So what picture would I draw to demonstrate what not one-to-one means?
Like 2 to 1 or 1 to 2?
Yeah, degenerate map. So that's not injective, that's degenerate. And then surjective just means you're mapping everything over here.
Okay.
Okay? And these are the two criteria that have to be satisfied by a map in order for that map to have an inverse. Because think about it. If I were degenerate, what the hell does F inverse mean? I mean, yeah, this is F'd over to here, this is F'd over to here, but what the hell does F inverse do to this?
You're F.
I know, you're F. You're totally F'd up. I mean, what's that, Flournoy? That's what I like to say. Anyway, okay. So if it's not one-to-one, there's no way there's a well-defined inverse. But also, if it's not surjective, then, well, what's the inverse acting on this? Because there's nothing over here to map it back to.
Okay.
Okay? So these are the two criteria that any map has to satisfy in order for there to be a well-defined inverse. And we're just using that in this situation. Now, normally you have to satisfy surjective and injective. Okay, for the reasons I just showed you. However, for linear transformations, they're not actually acting on elements in one space and returning elements in another space. They're taking elements of a vector space and giving you back elements of the same vector space. Okay? So there's a sense in which this is already surjective. So really, as long as a linear transformation on a vector space is injective, it's invertible. But of course, that's basically where this theorem came from.
So why does that second condition have to exist if it's?
Because for infinite dimensional linear transformations, it's not as obvious.
Yeah.
So for the finite case, all we have to focus on, if we have a linear transformation and we want to know whether it's invertible, all we have to do is think about condition A here or this theorem. We don't have to worry about surjectivity.
When we say like infinite, are we saying like
Infinite
the
dimensional.
Okay, so saying like you could put any arbitrary coefficient on t squared, that doesn't make it like infinite if it's
No. The field is infinite. It's the dimensionality of the vector space.
Okay.
And that's basically the number of vectors that is in a basis of the space.
Okay.
Where the basis of the space we defined a lecture or two ago. Okay?
That's also the number of elements in a vector, right?
Well, when you say the number of elements in a vector, what do you mean?
Like a two-component vector would have two basis vectors.
So that's what the basis is being used for, is to basically decompose any vector into a sum of vectors, each of which is a basis vector times some element of the field. But yes. Okay. So if A inverse exists, and that's a big if because we don't always have, you have linear transformations that don't have a well-defined inverse. Okay? But if A does exist, then it is linear as well. So it satisfies all of the defining properties of a linear transformation. Okay? Moreover, if A inverse exists, it doesn't matter what order you apply A and A inverse, you're always going to get the identity. So a linear transformation always commutes with its inverse. Okay? How are we doing? Good? All right, sweet. Now, I would like to complain for a moment. Because I imagine that for D on Pn, which we just argued there was no inverse, what about defining S on a vector X in Pn as 0 to T, X is a function of U, du? Let's check it out. On P4, if X is T squared plus T, then dsx is d times the integral from 0 to t of u squared plus u du. And you can all do that integral. Remember, d is just d by dt, so this is going to give me t squared plus t. And similarly, if I instead do sd on x, That is, if I reverse the order of the differentiation and the integration, I will also get t squared plus t. So it seems like integrating is the inverse of differentiating. If I start with t squared plus t and I apply the operation of d times s, I get back t squared plus t.
What if you had a constant though?
What if I had a constant? It's always them damn constants. Yeah, if you throw a constant in there, dsx equals t plus 1, acting very much like the identity, but sd equals t. Okay? So the thing is, you can have combinations of operators which seem as if they are exhibiting an inverse relationship. But you have to satisfy all of the properties, including the fact that a transformation and its inverse must commute. You must get the exact same thing if you reverse the order, which you're clearly not getting here. Okay? So if all you ever did was check this one, you might say, oh yeah, S is the inverse of D. Well, that's in that order, but you have to reverse the order and see if you get the same thing, and in this case you don't. Okay. All right, so let's see. Okay, so to finish up, some more properties that are useful. If A and B are invertible, then so is their product AB with AB inverse equaling B inverse A inverse. Okay? This is one of those interesting things where you reverse the order of the transformations if you want to break down whatever you're doing to them into them individually. But this should be obvious, right? I mean, AB inverse AB okay. 2, if A is invertible and alpha, an element of the field, doesn't equal 0, then alpha A inverse equals 1 over alpha A inverse. Okay, that should be somewhat obvious. And then if A is invertible, then A inverse equals A. Okay. Now please don't take A inverse to mean that. It's not that simple. Okay? It can be that simple depending on what linear transformations you're dealing with. You could end up with just numbers. But in general, it's not that simple. All right. Now we're going to go into more on inverses after we've introduced matrix land, which I'm about to do. But are there any questions so far? let's see how matrices enter into the story. And once we understand that, we can relax and just talk about matrix land, which is an exquisite place. Recommend you all go there sometime. And you could laugh even if the joke's not funny. Thank you, I appreciate that. Oh man, what is it? Is it so late in the day you're all worn out and you're just like, I can't laugh. Oh, I'm getting it out of it. Yes, that's actually it. That's, I've heard of it. Okay, fine. I won't laugh at you if you won't laugh at me. Which will probably be relevant when I'm grading stuff. Maybe, I don't know, probably not. Okay, so recall from isomorphisms, we realize that any vector can be represented by an n-tuple, where n is the dimension of the vector space over the field. That is an element of the vector space over F is isomorphically mapped to an n-tuple over elements of the field, or of elements of the field. Okay? And remember what an n-tuple is? You remember? Okay, good. Huh? It's a set of, it's a set of n field values. Yeah. Okay? Now, I'll come back to that. Okay, so linear transformations. If any vector space can be isomorphically mapped to an n-tuple, what do you think any linear transformation can be mapped to? Oh, you left. Man, you slipped right out. Yeah, goodbye. Anyway, what would you guess any linear transformation can be mapped to? An n by n matrix. Okay? So, once again, any vector space, period, can be mapped isomorphically. It's identical to an n-tuple. That's this, it's like a column vector. Therefore, any linear transformation which acts on the vector and returns another vector in the space can be mapped to a matrix. Okay? So, what I'm going to do is I'm going to kind of set this up, and I'm going to hopefully demystify his notation in the book a bit. So let me start by doing the following. So first of all, let's take a vector. Now, what I have not done yet is I have not created a basis, coordinate system, anything like that. I've just drawn a vector, and this is accompanied by other vectors that I can draw. Okay, so vectors pointing somewhere on the board. It turns out that with this definition of vectors, you can show that this satisfies all of the defining properties of a vector space without introducing coordinates or basis vectors. So for example, you can prove that this forms an abelian group with 0 as the identity, with sum as the operation. How do you do that?
You just draw a bunch of arrows. So like, you can draw an arrow and then add it to another arrow just by drawing the next arrow, like to
Yes, exactly. So it's funny, when we teach graphical addition of vectors in Physics 100, we're like, I'm going to be so badass and teach you about component-wise addition of vectors. But what we didn't realize in teaching Physics 100 was that the graphical addition of vectors, that's the defining property. You don't need coordinates in order to do that. You can just take vectors and you can add them together and get the resultant vectors without ever defining a coordinate system. That's pretty badass, pretty fundamental, okay? However, as you are all aware, it becomes rather convenient in many instances to introduce a coordinate system. A talking coordinate system, I mean. Or a humming coordinates, I don't know what the hell it is, okay? So we have a coordinate system, but with that coordinate system, we can now define a coordinate-adapted basis of the vectors. So we can define, oh, sorry, it doesn't have to be that big. A basis vector aligned with one coordinate and a basis vector aligned with another coordinate. And I don't have to pick these to be orthogonal. I just happen to. Okay? So now, and you'll appreciate this in just a moment. Now that we have a basis, we can say that x is alpha 1 times the basis vector x1 plus alpha 2 times the basis vector x2 okay? But, and this is hopefully where I'm going to make this point abundantly clear, this is isomorphic to alpha 1, alpha 2. That is a 2 tuple over R, or RT. Okay? So after you've established a basis in the space, you can completely identify all of your vectors just by giving these two coefficients. But these constitute a 2 tuple. Okay? Now, I want you to be very cautious about this. For example, if we define x1 as 1, 0, and x2 as 0, 1, then x is alpha 1, 1, 0, plus alpha 2, 0, 1, which gives me a 2 tuple, okay? But when you write it like this, you're kind of forgoing the fact that, well, actually, there's a basis vector times a number and a basis vector times a number, and this is just two numbers. So this analogy is basically using this isomorphism, okay? Everybody on board with that? Because otherwise what I'm about to show you will be confusing. Okay, so a linear transformation acts on what? A vector. Good, good. So a linear transformation can act on a basis vector, and if I know the components of A, which will just be A, I, J, where this labels the row, this labels the column if I'm listing this as a matrix, A on xj is the sum from I equals 1 to 2, in this case if we're dealing with a 2 by 2, of A, I, J, X, I. Now I want you to think about that for a minute. Anyone who has taken general relativity with me, or possibly saw this in particle physics, I can't remember our matrix stuff in particle physics. Hopefully you remember that if you're multiplying if you want to do matrix multiplication, the two indices that are being summed over have to be immediately adjacent. But this is aij times xi. So is that legit? Well, watch, okay? So this is telling me how the basis vectors transform under the linear transformation A. Then I can say, okay, all right, then A acting on X, which is an arbitrary vector, is the sum from J equals 1 to 2 of alpha J times the sum from I equals 1 to 2 of Aij xi. So, what this linear transformation in this expression is doing is it's taking the vector x and it's leaving these coefficients the same and it's transforming the basis.
Could you say that again?
What this linear transformation is doing to the vector x is it's leaving these coefficients the same, but it's transforming the basis. Okay? So this is the same alpha, but with x prime, a new basis. However, folks, let me see. Oh. We can rearrange this. To give an expression like that, which is alternatively giving new coefficients and expressing the vector in terms of the original basis.
Is this just a funky way of writing matrix multiplication?
Yes, yes.
Okay.
But this is what I'm saying. In another class in GR, which some of you have taken, you are taking a matrix and operating on an n-tuple with it. And the notation for that is you take the elements of the matrix and you sum over the column part with the components of the vector. Okay? But that's different than if you're transforming the basis vectors. In that case, when you do the sum, you're summing over the row part of the matrix combined with each vector.
I'm a little confused here that it seems like we're getting rid of the n-tupleness of this with that second summation. Like if we're summing over J, aren't we like losing that sort of vectoriness of it?
Well, no, if you sum over J here, you're just going to be left with I.
Yeah.
And then you're going to have a sum over alpha prime I, xi, which you can write as an n-tuple. Or, I mean, yeah, it is an n-tuple, if you just focus on the alpha primes. So, again, this is largely Well, so, all right, so if we take a vector space, okay, we know there are two ways to affect a rotation, right? We can do an active versus a passive. And if we do an active rotation by this angle, then the picture becomes this. If we do a passive version, then the picture becomes this. Okay? Well, the B prime in each case is the same. Okay? Here, you're leaving the basis alone, so the coefficients have to change. Here, you're transforming the basis. Okay?
I'm fine with it conceptually, I'm just confused about like, I guess like the summation itself, cause like when I think about it, you know, doing like when you're doing it with tensors, you'd only sum over the thing, like the matching index.
Yes.
But we're summing over both indices here, which makes it seem like you lose that structure.
No. No. So what you're thinking about from your memory of general relativity is what is happening to the components of a tensor. Remember, and I'm sorry, this is going down this way. Remember, early on, I wrote a tensor as components times bases. And altogether, the tensor has no indices. You only get the indices labeling the various components when you break it up into a basis and then its components, okay? But then what we realized and what I demonstrated in that class is that all of the transformations that you want to do, they act one way on the element, on the components, and then they act in an inverse method on the bases so that those two transformations actually cancel. So if you do a transformation, the actual object, so this is actually kind of bullshit, okay? Because actually, you know, well, yeah, I don't want to say that story is bullshit. But in any case, the actual object itself, the tensor itself, forget about assigned components and a basis, okay? The actual tensor itself is invariant. And when you do a rotation, you're rotating the underlying coordinate system. So your components have to change one way and your basis has to change the other way. And that's exactly what's happening here as well. I'll have you do this on a homework problem. That should make it clearer. Okay? But there you go, folks. If you... So, I mean, notice this has no index notation whatsoever. This is a vector from the vector space, and this is a linear transformation. We're going to elect to represent this by an n-tuple and therefore represent this by a matrix, but we don't have to. Okay? If you want to do that, you can either transform the basis or you can transform the components. Transforming the components is the way to go. Okay, because normally we just establish a basis and then we just use that basis for everything. So if you follow what's happening to the components throughout a story, then you're fine. Okay? And this is just ordinary matrix multiplication. This is literally, if you write this as a matrix, you multiply this column vector by it. This is not. That's what I'm trying to tell you. Yes?
So regardless of how you do it, the transformation stays the same, right?
Yes. Yeah. Okay. I'll have you pan this out in a homework problem tonight. Okay? But what I want to do now is I want to give you an example using that good old, not obvious vector space, an n-tuple space that is defined by polynomials. Okay. So, and by the way, this might or might not be obvious, but I'll write it up here anyway. You know, if A has elements where the first index labels the row you're in, and the second index labels the column you're in, okay? And X has interval components alpha 1 and alpha 2, then, and obviously we're not using the Einstein summation convention here. We could, but we won't. Then this just means I sum over the j's, so I have A11 alpha 1 plus A12 alpha 2, A21 alpha 1 plus A21 22 alpha 2, which is exactly what I would get if I took this matrix and multiplied this. Okay, that's all the summation convention is giving me there. Okay, so let's consider an example. Okay, so consider P1, it's the set of linear at best functions of t with a representative element alpha naught plus alpha 1t. Now that's the most general element of P1. And good old d is d by dt. Okay? Now, what is dx equal? Joel. You gotta wake up, man.
Alpha 1.
Yeah, it's equal to alpha 1. Okay? Everybody on board? So, I promised you that x's can be intuples. So x could be a tuple, a two-tuple of alpha naught alpha 1. D should therefore be representable by a,
Matrix.
what dimension?
2 by 2.
2 by 2 matrix. Exactly. So let's bang through that. So dx is a 2 by 2 matrix times alpha 0, alpha 1, which I want to give me back alpha 1, 0, because notice this is a constant. It's not multiplying a factor of t, so it belongs in the upper space. Well, what is d?
0, 1, 0, 0.
Exactly. This is the matrix, the isomorphic matrix to the operator derivative acting on the vector space P1. Okay? Now, this is using the basis 1 and t. Obviously, when I write this as this two-tuple, this thing is the thing that's multiplying number 1, this thing is the thing that's multiplying t. So I can say 1, 0 corresponds to the number 1, and 0, 1 corresponds to t. Okay? Let's just quickly ask, suppose instead we wanted to use 1 plus t and 1 minus t. Okay? That's a perfectly good basis for this P1 space. Okay, these are clearly linearly independent. What do you think D looks like in this case? Well, let's do it. So first of all, we have to write what a vector x looks like. Now, I want to use the same vector x here. Okay? So the x is going to be the same, but whereas this one's written in the 1t basis, I want to write this one in the 1 plus t, 1 minus t basis. That's pretty straightforward. This is 1/2 alpha 0 plus alpha 1 times 1 plus t plus 1/2 alpha 0 minus alpha 1 times 1 minus t. If you multiply that out, combine all the terms, this is going to give you exactly this. But this is now expressed in terms of the 1 plus t and the 1 minus t basis. Does that make sense? You follow? Good. Dx should be alpha 1. But alpha 1 is just 1/2 alpha 1, 1 plus t, plus 1/2 alpha 1, 1 minus t. Dx is alpha 1. That's the same thing we set up here, okay? However, this is expressed in terms of the 1 and t basis, and we need to express it in terms of the 1 plus t and the 1 minus t basis. Well, there you go. Does everybody see that this will reduce to this? Madison, you're squinting your eyes.
I'm squinting because I'm wondering if that it should be like a minus in the middle there, but I don't feel confident about that.
No, it should be plus. So,
Okay.
yeah, the alpha 1, the t term is going to disappear. And you're just going to be left with alpha 1. Okay? Now, we can find the matrix because dx should be a matrix times 1/2 alpha 0 plus alpha 1, 1/2 alpha 0 minus alpha 1, and it should give me 1/2 alpha 1, 1/2 alpha 1. Okay? The matrix acting on x, this is x in the 1 plus t, 1 minus t basis, is this coefficient times the 1 plus t basis vector, which we can assume is 1, 0. So we just have this coefficient in the top, and then we have this coefficient in the bottom. And the result has got to be this, which is just the matrix version of this, or the n-tuple version of this. 1/2 alpha 1 times the first basis, and 1/2 alpha 1 times the second basis. What's D?
1/2 minus 1/2, 1/2 minus 1/2.
Yes. Exactamundo. Okay? So, you know, I love this example because derivatives of functions, I mean, who the hell thought they would be vectors, but they are. Okay? And this is going to become more generalized as we relax into infinity because we're going to be able to cover a lot more than just polynomials. All right? Okay, so oh yeah, we're done. Okay, so I'll start out next time with a few more interesting features of matrices, and then we will turn it over to a new topic that is determinants and so forth, and then we'll carry on from there. So remember, I'm holding office hours from, what did I say, 7 to 9 tonight? 7 to 9, that'll be on Zoom. So I'm just going to go up to my office and sit in my office and open up Zoom. But I'll open it up at 7, okay? So you're welcome to join me, ask me homework questions. I'll try and go ahead and get the next 2 homework questions on the course webpage before 7, so you can go ahead and have a look at those. And I'll update the course website with my office hours. Okay? All right, thanks everybody.
I just talk to you real quick, Dr.